So this is the outline of my talk. So first we'll see some preliminary results and definition which will be useful throughout the talk. Then we'll see the motivation to our problems, followed by studying two types of integral operators on the Bergman space over the upper half plane. And then with the help of this, we will be able to construct at the end C-star algebras of analytic functions on these two domains. So first one is the upper half plane, and C minus I will be defining later. Okay. So if X is a major space with a sigma finite major nu, then we have the L2 of X is the Hilbert space of all new measurable functions, complex valued functions on X, which are square integrable against the major nu. So and we also define a Euler product on it in a usual sense. Now, if we consider any new measurable complex valued function on X, then its essential range consists of all those elements A in C, such that given any epsilon, the measure of this set is positive. And if we consider L infinity of X to be the collection of all essentially bounded new measurable functions on X, then it is well known that it is a Banach space, and the norm is given by this. Now, Malay has already defined what is C-star algebra, but let me redefine it once again. So, if we have A to be an algebra over C, so we can take field to be real numbers or complex numbers, but here we will be taking C throughout the talk. And if I have an algebra with the multiplication operation, which also satisfies this norm condition, then such algebra is known as a Banach algebra. And along with this Banach algebra A, if we also have a star operation, unary operation on A, which satisfies these 5 conditions, then such algebra is known as involutive Banach algebra. And additionally, if this involution operation, sometimes also known as adjoint operation, if it also satisfies this condition, which is known as C-star condition, then such a involutive Banach algebra, we call it as C-star algebra. So we have the well-known examples. So in case of function space, we have X to be a major space, then L infinity of X consists of all essentially bounded functions on X. It is a C-star algebra, and for this L infinity of X, we have that F star, this multiplication we defined as pointwise multiplication, and the star operation what we have is the usual bar conjugate of the function. Similarly, if we want to see in operators, bounded operators, then we can take L2 of X, and if we take all bounded multiplication operators on L2 of X, then we have that this collection forms a maximal commutative C-star subalgebra of B of L2 of X. In fact, it is a von Neumann algebra. And with respect to the map gamma, which takes M to the multiplication operators with multiplier M, we can also think L infinity of X as a von Neumann subalgebra of B of L2 of X. A pointwise multiplication. This one? This is for defining domain of this operator, because initially I am not considering M coming from L infinity of X. So it is just a some domain, and then if we are able to extend this map as a bounded operator to whole space, then yes. So it is known that this operator is bounded if and only if M comes from L infinity of X. Yeah, so since we will be at the end, we'll be seeing C-star algebras of analytic functions, which are also related to some very special type of Hilbert spaces, which are known as reproducing kernel Hilbert spaces. So let us first see what are reproducing kernel Hilbert spaces. So here F is a field which is either R or C, and X is a non-empty set. Then F of X comma F denote the functions from X to F, which is a vector space. And if I consider H to be a non-empty subset of this collection, then it is said to be a reproducing kernel Hilbert space, and simply sometimes RKHS if it has these 3 properties. So first of all, it is a vector subspace of this collection. Then we put an inner product on it so that it is a Hilbert space. And the very important property is for each x coming from this capital X, we have that the evaluation functional Ex, which takes f to f of x, is a bounded linear function. Now, since we are in a Hilbert space and the functional is bounded, Rees representation theorem says that we have a representative in H, we denote it by Kx, such that the action of Ex on F can be given by inner product of F with Kx. Now, since Kx reproduces the values of functions at X, we call this Kx as point reproducing kernel at X. And using this, we can define a reproducing kernel for H by K of X comma Y equals to Ky acting at X. For example, we have the Fock space on Cn, which consists of all holomorphic functions, which are holomorphic functions in L2 with this Gaussian weight. So it is well known that it is RHS and the kernel is the exponential function e power ZW bar. Similarly, if we take the upper half plane and if we take the Lebesgue measure, which is the restriction of measure of C to pi, then the collection of all holomorphic functions in L2 of pi is also a reproducing kernel Hilbert space. And here we have that the kernel is minus 1 by pi z minus w bar whole square. Okay. Now, due to the reproducing kernel Hilbert space nature of the Fock space, we have that given any linear operator on the Fock space, it can be uniquely represented by an integral operator given by equation 1, where the kernel function kt is an entire function on C2n which satisfies these two conditions. So one can ask, can we characterize all these entire functions so that the operator t defined by equation 1 is bounded? So in attempt to this, we consider a very special type of kernels, and for that we studied the boundedness. So what we could take is, we started with phi coming from the Fock space. Associated to this phi, we consider this kernel, which is in the red color, and we formally define the operator h phi. And we could show that this h phi is bounded if and only if there exists an L infinity Rn element m such that phi and m satisfies this integral equation. Moreover, we also have that the operator norm of h phi is same as essential supremum of L infinity of Rn. But in this paper, we did not discuss anything about the symbols associated with this operator HP. But recently, Ma and Zhu, they could show that if we consider all these symbols phi, all these symbols f, so that this h suffix f is bounded operator, then they could give a C-star algebra structure to this symbol. They showed that with respect to this multiplication operation and the norm given by this. So this is same as the operator norm of the associated operator, and with this adjoint, we have that it is a C-star algebra. So in this case, our adjoint is f of z bar, because this adjoint will not work since we are in an analytic function, the conjugate will be anti-analytic. So also there was an open question posed here. Can we say something about a very concrete C-star algebra on a unit disk? Since this is on full C, what can we say about a unit disk? So in this direction, we answered that, but not on the disk. Since we have that the disk and upper half plane are biholomorphic, so it is enough to get C-star algebra structure on one of the domains. So here we consider the Bergman space A2 of pi, and similar to the Fock space, and due to the reproducing kernel Hilbert space nature of A2 of pi, every linear operator will have this form, and the integral kernel is an analytic function on pi cross pi, such that the kernel should also satisfy these two conditions. In fact, these two conditions also guarantees that the operator what we define formally is a densely defined operator. So in this direction, first we consider the analytic function phi on pi. Then we consider the kernel function k phi using this phi, and we also need these two conditions that the phi should satisfy. So associated to such phi, we formally define the operators v phi with this kernel, and we were able to show that such a v phi is bounded on A2 of pi if and only if there exists an essentially bounded function sigma on R plus, where R plus is a positive real line, such that phi and sigma satisfies this integral equation. Moreover, we have that the operator norm of V pi is same as essential supremum of L infinity of R plus. But what else can be said is, if we consider the collection of all these V phi, it forms a maximal commutative sister subalgebra of B of A2 of pi. And it also coincides with the well-known class of vertical operators on A2 of pi. So studying these operators V phi has two advantages. First of all, we were able to answer this question in a particular, for a very special type of integral kernels. Secondly, we were able to provide concrete integral representation for the vertical operators on A2 of. Later on, we consider C minus to be complex plane minus positive real line, and this collection defines consist of all those analytic functions on C minus, such that the kernel K phi defined in this fashion satisfies these two conditions. So for such phi, here we consider the operator A phi in this fashion, and as we have seen in the previous case, we could show that these operators are bounded if and only if there exists an essentially bounded function sigma on R, such that phi and sigma satisfies this equation 8. And moreover, we also get that the operators A phi has its operator norm same as essential supremum of sigma. Again, as in the case of vertical operators, we have that this collection is a C-star subalgebra of B of A2 of pi, and it coincides with another class of operators which are widely studied on A2 of pi, known as angular operators. So where we say an operator T on B of A2 of pi, in B of A2 of pi to be angular, if it commutes with all these operator DH, which are also known as dilation operators. And here I forgot to mention that we have that a linear operator T to be vertical if it commutes with this real translation H suffix H, these operators, which are unitary due to the fact that the measure on this is translation invariant with respect to real translation. Okay. So again, as in the previous case, here we were not able to show some some properties of the symbol functions for V phi as well as A phi. But now what we have is, if we consider these symbol functions such that the operator V phi is bounded, then we have that they have this structure, and we showed that this collection omega 1 with respect to usual vector addition and scalar multiplication, it is a vector subspace of O of pi, and the norm on this is nothing but the operator norm of V phi, and we were able to get new type of adjoint operation. Now it is it can be seen that this adjoint will not work, because when Z is in the upper half plane, Z bar will go in the lower half plane. So obviously this doesn't make sense. So what we have is something different. It's minus Z bar, which again comes up in the upper half plane, and then we can define this star operation. Similarly, we have this multiplication formula. So what can be seen is, inside this phi1, we have the algebraic mean of Z and minus eta bar, whereas inside phi2, we have the algebraic mean of Z and eta. And although we have that these symbols have some kind of structure, means each phi is associated to some m, here that m will not appear. It is completely implicit. And we can also see that the identity element in this is the 1 by z square. So as in the Fock space case, we wanted the symbols also to belong to the space, but in this Bergman space, we may not have that condition. And this is the example, because 1 by z square, it is an analytic function on pi, but it doesn't belongs to A2 of pi. And now similarly, if we consider the angular operator A psi, which are defined earlier, and if we consider those symbol functions, then what we could show is they also forms a maximal commutative, means they also forms a commutative sister algebra. So again, we have the linearity, which is coming from the linearity of all holomorphic functions on C minus, and the norm is same as operator norm. But what is different is the star operation, how we define, and the multiplication operation. So in the previous case, we were dealing with the algebraic mean, whereas here we are dealing with the geometric mean with respect to 1 by eta bar and eta. And one can easily calculate that this psi naught is an identity element in this case. But what is more interesting in the second case is we started with the operators which are defined on A2 of pi, but at the end we end up with the sister algebras on domain which is not pi, which is something different, C minus. And there is something which is not yet explored in this direction was these multiplication operation are irrespective of this sigma, this structure. Means so it is natural to ask, can we get the maximal subset omega 1 dash of these holomorphic functions which contains omega 1 such that this multiplication operation can be extended to that subset. And similarly for the symbols coming from A side. So these are the references. So in the first one, we consider the H5 operators. Later, the symbols associated with that was shown to be a sister algebra in this paper. Now, in the second and third paper, we consider vertical operators and angular operators. And the symbols associated with that was studied recently in this paper, which is still under review. Yeah. Thank you.